So this is the introduction to chapter 11 on integration in the year 13 content. I'm going to just run through the skills check questions first. I'm going to give you an opportunity in the video to pause and have a go at those questions, and then I'm going to walk through them step by step. It's really important that you do revisit those old skills because they will become part and parcel of what we do through the integration chapter. They'll be useful in a variety of different places. So do take your time to go through this video and have a good go at the questions. Don't just skip this because you've done it recently or you've done it before. The overview of integration is, first of all, that we're going to explore how to integrate slightly more complicated functions. There's a whole load of basic, what we call standard integrations that we can complete now that we've investigated differentiation a bit more. And we've also met a couple of differentiation rules which we can reverse engineer to do some more complicated integration, and we'll have a look at those as well. We're going to put trig into the integration stuff as well, which is obviously lots of fun, trying to spot the right trig identities to use. And we're also going to have a look at an entirely new strategy for integrating things. In fact, a couple of completely new strategies for integrating things. The final section of this chapter on using the trapezium rule to approximate and then solving differential equations, we're not going to tackle in this chunk of time in January. We will come back to them a little bit later on in year 13. So we're going to get up to integrating to find areas under curves, and we're going to pause there. So we've got these prior knowledge skills checks. At this point, it would be really good to pause the video, have a go at these on your own, and then hit play, and I'm going to go through these answers for you. So, part A, we've got a function inside a function. This is a chain rule question, but because it's such a simple chain rule question, I wouldn't expect you to need to do the chain rule for it. We're going to take the power 6 and bring it in front, and therefore we're going to lower the power down to 5. And we're also going to multiply by the differential of what's inside. So we need to multiply by 2, because if I differentiate that inside function, I get 2. So tidying up, that is 12 times by 2x minus 7 to the power 5, and that's it. B, sine differentiates to cosine, so our answer is going to be of the form cos 5x, but again, this is a little chain rule question. We also have to multiply by the differential of 5x, which is going to be 5 cos 5x. And then C, if you differentiate e to the x, you get e to the x still. If you differentiate e to some constant times x, in this case 1/3, you get the constant multiplied by e to the x, 1/3 e to the x over 3. All fairly straightforward, all covered in chapter 9 of this year. We're also going to need, obviously, to use some of our standard straightforward integration skills. So again, pause the video, have a go at these two questions, and then hit play and see the answers. Okay, so part A, if I want to integrate f of x, which is 8x to the half minus 6x to the minus half with respect to x, what I do is, because it's just a standard polynomial, I raise the power by 1 and then divide by that new power, the exact opposite of differentiating. So I'm going to get 8x to the 3 over 2 divided by 3 over 2. Take away 6x to the 1 over 2 divided by 1 over 2 plus our constant from integrating, because remember, if you differentiate constants, they disappear. So when we have to integrate, we need to pop that constant back in because we don't know whether it was there or not. And this tidies up. 8 divided by 3 over 2 is going to give us 16 over 3 x to the 3 over 2. And then 6 divided by a half is going to give us 12 x to the half plus some constant c. And then part B, I'm now doing the exact same integration, but I have limits of 9 and 4. So I substitute 9 in, So I have 16 over 3 times by 9 to the 3 over 2, take away 12 times by 9 to the half, take away, and then I substitute 4 in. So 16 over 3 times by 4 to the 3 over 2, take away 12 times by 4 to the half. And remember that when we put limits in, the plus c disappears because I have a plus c in both brackets, they just cancel each other out. And at this point, you really ought to grab your calculator and use that because it is much, much easier to do this on a calculator. So 16 over 3 times by 9 to the power of 3 over 2, take away 12 times by 9 to the half. It's going to give us 108 here. And then 16 over 3 times by 4. To the power of 3 over 2. Let me try that again. To the power of, there we go, 3 over 2. Take away 12 times by 4 to the power of 1 over 2 is going to give us 56 over 3. And then I just need to subtract those two things. So 108 take away 56 over 3 is going to give us 268 over 3. And we're done. 268 over 3 is our final answer. Now, so we're also going to need to be able to tackle partial fractions, largely because integrating a partial fraction like this is a mess, but if we split it up into its two smaller, tidier parts, we can integrate them separately, and that's a lot simpler. So again, press pause on the video, have a go at this, and then press play and I'll go through the answer. So, what we need to remember is 3x plus 22 over 4x minus 1 and x plus 3 can be rewritten as something over 4x minus 1 plus something else over x plus 3. And if I can do that, then if I combine these two, the a and b fractions, to get a common denominator, what I end up with is 3x add 22, the numerator, has to equal a multiplied by x plus 3 add b multiplied by 4x minus 1. Denominators will be the same, they can all disappear. This is going to work if these things are equal. And now I need to find a and b, and we do that by choosing a sensible substitution for x. So if I pick x equals negative 3, that's convenient because it makes this bracket worth 0, so this whole term is worth 0, and that tells us x is minus 3, so 3 lots of negative 3 add 22 equals nothing plus b lots of 4 lots of negative 3 take away 1. And we can tidy this up. This is negative 9 plus 22, so that's 13. And then this is negative 12 take away 1. This is negative 13b. And that means that b has to be negative 1. Now I know b is negative 1. I can pop it back into this equation up at the top. So I have 3x plus 22 equals ax plus 3. Take away 4x, add 1. Because I know b is negative 1, so I can just plop all that in. And then, if I make myself a little bit more room, in that case, I end up with 7x plus 21 equals a lots of x add 3. And hopefully from here you can see really easily that a has to be 7. Sometimes it's more efficient to do a second substitution, but I didn't do that largely because the bracket next to b, to make this 0, I would have had to put a quarter x in, and substituting a quarter in, it would have been a bit more fiddly than just playing around with that algebra. So now that I know what a and b are, I can say that my expression from the start, 3x add 22 over 4x minus 1 times x plus 3 equals 7 over 4x minus 1, take away 1 over x add 3, because a is 7 and b is negative 1. And there we go, we're done. Partial fractions. And then the fourth point, which the textbook picks out as being a useful thing to remind yourselves of, is this, finding the area under a curve. So again, hit pause, have a go at this question, work your way through, and then press play to see whether you're working out and your answer match. Okay, so to find the area under a curve, we are needing to integrate between these boundaries. So between -1 and 2, we need to integrate x squared plus 1 with respect to x. That means that, well, if I integrate x squared, I get x cubed over 3, and if I integrate 1, I get x. And I want this to run between -1 and 2. Remember, I don't need the plus c now, because I have a definite integral between two values, so the plus c doesn't matter. So this is 2 cubed over 3 plus 2, take away -1 cubed over 3, take away 1. And again, this is the point where we bring our calculator in and we just plug all of that in. So 2 squared, 2 cubed over 3 plus 2, take away -1 cubed over 3, take away 1. And I press equals and I get 6. And that equals 6. We don't have any particular units. The textbook specifies this as 6 units. You don't actually need the word units in there, but it's taking up 6 of those square units on the grid. Remember, when you're using your calculator, this expression on the calculator screen needs to look exactly the same as what's on paper, and when you've got negatives, it's really sensible to substitute using brackets around your substituted value. If I don't put brackets around things, especially when terms are being squared and so on, sometimes you end up with muddled up minus signs because the calculator does things in not quite the order you expect. So just make sure you're being really accurate with your calculator, as well as getting all the other stuff.